Welcome back, everyone. Now for vectors in the real world, three-dimensional space. Okay. Not only do we have ourselves an x-axis and a y-axis, but we also can come out this way, or we can go farther away from ourselves. There's your z-axis. Now everything is relative. I mean, however you want to put your x, y, z axes is really kind of up to you, but I would like to try to keep some sort of consistency with the class. You notice here, this is a great diagram just to show you the spherical representation of a vector, right? I can, not only do I have here you can see how the x, y, z is a little bit different, but you have, something on the x, something on the y, and something on the z, and then from there you can create, wherever this vector is pointing. So anyway, consistency for the class, why don't we do it this way right here, okay? We're used to looking at the xy axis just as it is here. You have your positive x, your negative x, your positive y, your negative y, and we'll just treat coming out towards us as the positive z and going away from us as the negative z, okay? How do we name these vectors? Well, we don't have an ordered pair anymore. What we have is an ordered triple, okay? We have ordered triples, because there are 3 numbers instead of 2. Okay, so it's an ordered triple. And the way so instead of xy, it's going to be xyz, xyz. But how do we get that xyz? If you remember from before, let's hold on, let's do this. This right here is the tail, okay? And this right here is the head. And let's call this one x1, I'm sorry, I want to call the tail x1, y1, z1. And the head we're going to call x2, y2, z2. Okay? You start at the tail, you end at the head. So we'll call the tail 1, 1, 1, and the head 2, 2, 2. All right, well, yeah, let's move this now. The way we label that vector is, it's always, here, let me write this down. This was in your notes from the other day, but you start at the head. It's head minus tail. You subtract the x values from the x, y, z values from the head first. So it's going to look like this. It's going to be x2 minus x1, comma, y2 minus y1, comma, z2 minus z1. The other day it was just xy, so it looked like this. Well, now it's xyz. So you just expand it into the z values, that's all. So let's name this vector. Well, if you notice, the head, well here, what's the origin? We're starting at the tail is at the origin, so that's going to be a 0 on the x, a 0 on the y, and a 0 on the z. What about the head? Well, if you notice, we go 5 on the x, then we go 8 up on the y, right? Here's your 5 on the x and your 8 on the y. And then we go this way. We go out 3 units on the z. This point is going to look like this. 5, 8, 3. Well, let's figure out this vector. 5 minus 0. 8, oh, I'm sorry. Well, that's not what I wanted to do. Well, let's see if we can continue here. Sorry about that if you were copying it down. Well, I want to do, whatever. I want to do 8 minus 0, comma, and then I want to do 3 minus 0. And that's going to give us a value of 5, comma, 8, comma, 3. And if you remember, that's what we should get, 5, 8, 3, the same value as the head, because when we subtract these values, what this tells us is what xyz value would the head be at if the vector was translated back where it started at the origin. Since ours already started at the origin, we got 5, 8, 3 back. Now for the magnitude of this thing. Let's just move that over there. And see if I can move that. Okay. So the magnitude is the length of this vector. And what we need to do is figure out what the vector is, the xyz value, and that we just did. We figured out it was 5, 8, 3. All right, well, the magnitude is, well, just like before, let's do vector AB. All right, I didn't know what, I'll call this A and B. I didn't really give it a name yet. and that would be vector AB. You could also just call it vector A. It doesn't really matter. But the magnitude is the absolute value. That's the magnitude of the vector, and it would be the square root. Well, before it was just x squared plus y squared, but now we have a z, so it's plus z squared. It's as easy as that. Okay, same formulas. You're just adding the z value. Let's see if we can figure that out. So our x was 5, our y was 8, and our z was 3. Oops, squared. Which equals 5 squared is 25 plus 64 plus 9. And that's going to give us a value of, what do you get there? Hold on. Looks like that's going to equal 98. Okay, and you can figure that, you can simplify that if you want, but whatever. The magnitude is radical 98. That's how long it is. These operations are all the same. Again, the only difference is you have that z value. So, if I were given vector A and vector B, and we'll call this one x1, y1, z1, and I guess we'll call this one x2, y2, z2. Well, if I'm going to add these two, vector A plus vector B, you got it. All right, before it was just x1 plus x2, comma y1 plus y2, but now it's also z1 plus z2. Subtraction, same thing. Okay, subtraction, we have vector A minus vector B. It's going to be the exact same thing, you're just going to have subtraction. You're subtracting, and you guessed it, you are subtracting. Nice. And for scalar multiplication, let's choose a different color. How about baby blue, or whatever this is? Scalar multiplication, I didn't say it up in our givens here. I forgot again. So, the givens, let k be any real number. So, I'm going to multiply a real number to a vector. So, if I have k times a, that's going to look like this. K times x1, y1, z1, and what you do with that is you distribute the k. And that's going to give you k times your x value, k times your y value. Oops, I'm sorry, 1. And k, I'm running out of room, but that is k times your z value. Just distribute the k. Pause this if you need to copy it down. All right, I don't expect you to write as fast as I'm going. So stop for a second. Let's do an example. How about we have vector A equals 7, 5, 6. Let's let vector B equal 4, 1, 3. And in our givens up here, we're going to let k be a real number. We'll let it be 3. Well, we are going to add a and b. We are going to subtract a and b. And then we are going to multiply 3 times vector A. We can do this. Okay, well, I'm not going to waste your time. This is so elementary. Once you know what you're doing, you're adding the x values, right? So 7 plus 4 is 11. And then you're adding the y values. I have a 5 and a 1. That's 6. And then my z values are 6 plus a 3. Let's subtract them. This is not commutative, so whatever vector comes first, if vector A, right here, hold on one second. If vector A comes first, well then the A values come first. 7, 5, and 6 come first. Actually, let me just, this I'll write out. I don't want anyone to miss it. Okay, this is good stuff right here. So it's going to be A minus B. So that's going to be a 7 minus a 4. That's going to be a 5 minus a 1. And that's going to be 6 minus 3. And that's going to give us 3, 4, 3. Nice. What's next? How about 3 times vector A? Vector A is a 7, a 5, and a 6. Distribute, and 7 times 3 is a 21. 5 times 3 is 15. And 6 times 3 is 18. There you have it. Again, pause if you need it. Now for those unit vectors again. Okay, we've already talked about it. We've talked about I and j. And today we are going to now accept the fact that we live in a three-dimensional world, and we are going to give ourselves a z-axis as well. That would be our positive z's, and going backwards from us would be our negative z's, if you will. Okay? And that would make these the positive x's, and these would be the negative x's. These would be our positive y's, and these would be our negative y's, okay? Depending on what graph you're looking at, again, that can be rearranged, but let's be consistent in class. X, Y, Z this way. All right, well, here are the unit vectors. Oops, I don't want that. I want this one. Oh, all right, hold on one second. I gotta get rid of that so I can move this sucker. Let's continue. Here are your unit vectors. Okay, the I and the j are in the same place, but now we know about the z-axis, so there's my k. All right, and that is just a length of 1 on the z-axis. Same thing as the other ones, it's just k is on the z-axis. Why do we do these things? Why do we find all these little vectors, these unit vectors? Not to get too off topic, but where we go with this is simple things like this. If we're trying to find current, for example, in water, each vector, the length represents the force of something. So how powerful is it? What direction are they going in? That's very important. And in this way we can track motion in a 3D world, and we can do things with it. All right? Keep your boat away from there. You're going to sink. You know, things like that. In the 3D world, we label vector I 1 for the x, 0 for the y, and 0 for the z. And for your vector j, we have 0x and 1y and 0z. Okay, we have to identify the z value. If you don't have one, it's 0. And for your k, that would be 0 on the x, 0 on the y, and 1 on the z. That's how that works. Writing vectors as the sum of unit vectors is the same in three-dimensional space. You just, again, have that extra z component, which would be the k unit vector. All right, well, say we wanted to write this as the sum of unit vectors. Let's give some values here. Let's say that this x value is 6. And let's say that this y value up here that it comes up to is 7. And this is going to be our positive z's. The negative z's would be going back this way. Okay, positive z, it looks like it's going to come out, say, will come out 3 over here. Okay, I just made up the numbers. Well, how can I represent that? This well, here, first I want to see if you can point this out. Okay, how do I graph this thing? Well, you're coming out, and then the best way to do this is kind of draw yourself some sort of rectangular prism. If you just watch what I'm doing here. Okay, it's not required, but if you want to have a little bit more luck drawing these things, there. Okay, it's not my best one, but what you're doing is you're coming out 6 units on the x, you're going up 7 units on the y, but then you're coming out towards us 3 units on the z, and that's why the vector head goes out here. Okay, so a prism will help you get this vector in the right place. But back to our ordered triple here, our x, y, z value. Well, we're at the origin, so that's 0. So it's here's my x, y, z. The x value is 6, I have 7, and I have 3. Well, this would just simply be 6i plus 7j plus 3k. And these are vectors, so technically you should have the little arrow over them. And we explained it the other day why it looks like this, but just revisit that if you will. There's your answer. Let's just do one more. Let's write this vector as the sum of unit vectors. The xy axes are irrelevant. It's different in this picture than it has been on the other one, but everything is relative like I've been saying. I mean, xyz that way, xyz, it's all relative. So, as long as you can identify what's your x, y, and z value, okay? Well, here on the x-axis I have a 2, so my x is 2. On the y-axis I have a 3, so my y value is 3. And on the z-axis I have a value of 5. So the ordered triple is 2, 3, 5. How do we write that as a sum of unit vectors? 2i plus 3j plus 5k. And why don't we use this vector symbol? Because we can. Again, whatever symbol you like is fine with me. If you don't recall how to rewrite why that, if it doesn't make sense why this is the sum of unit vectors, revisit the lesson from last night. We explained it there. Vectors in 3D space. What a deal. Alright, let's see what we got going here. We did vectors in 3D space just now. You took notes on it. Tomorrow in class, we are going to work on some practice problems. And we're going to study for quiz. I'm not going to give you the quiz tomorrow. You're going to study for it and take the quiz on the following class day. Okay, so don't get confused on that. We do not have a quiz tomorrow. See you then.